Hey there, it's Michaela, Math 241, Section 12, and we're back again today with a video, this time on irrotational and incompressible vector fields. Okay, we're going to be defining what it means for a vector field to be irrotational and incompressible. So, we're going to let F equal the vector field P, Q, R be a differentiable vector field from R3 to R3 and we can let A be a vector in R3. Then we can define F is irrotational if the curl of F at A equals the zero vector for all A in R3. Now we can think about this. When we talk about curl, this means the tendency for the function to rotate about a specific axis. So if there's no curl, then there's no rotation, meaning it's irrotational. And for F to be incompressible, the divergence of F at A must equal the number 0. Now, we can think about divergence in the context of fluid flow. So the divergence simply means the tendency for fluid to flow in and out at a certain point. So if there's no fluid flow, meaning the divergence is 0, then it's said to be incompressible, meaning that there's no change in that fluid density. And this is for all A in R3. An example of a vector field that is irrotational but not incompressible is the vector field G equals PQR equals 0, 10 minus y, 0. So to determine whether or not it is differentiable, we can take the partial derivatives of G. So the partial with respect to x is 0, because there's nothing in the x place. The partial with respect to y is -1, and the partial with respect to z is 0. So it is differentiable. Now, to determine whether it is irrotational, we'll compute the curl of G, and the curl of G is equal to the determinant of I, J, K, meaning the x, y, and z coordinates, of the partial derivatives and the function. This is equal, upon computing this, to the partial of r with respect to y minus the partial q with respect to z, the partial p with respect to z minus partial r respect to x, partial q respect to x minus partial p respect to y. Now computing this using our function, we have that the partial of r with respect to y is 0, minus partial q respect to z is 0, the partial p respect to z also 0, minus partial r respect to x is 0, minus partial q respect to x is 0, minus 0. So the curl of G is in fact equal to the 0 vector, meaning this is irrotational. To determine whether it's incompressible, we can compute its divergence, which is equal to the gradient of G, so its partial derivatives, dotted with the vector g. And computing this, we get that the divergence of g is equal to partial p with respect to x plus partial q with respect to y plus partial r with respect to z. Upon computing this with our function, partial p with respect to x is 0. The partial q with respect to y, however, is -1. And the partial r with respect to z is 0. So the divergence of g is equal to -1, which is not 0. Therefore, this function is not incompressible. An example of a vector field that is incompressible but not irrotational is the vector field H equals PQR equals y minus 4, 10, 0. So this is a differentiable function because upon computing its partial derivatives, we get the partial with respect to x is 0, the partial with respect to y is 0, and the partial with respect to z is also 0. So this vector field is differentiable. So now we can compute its curl. So similarly to last time, the curl of H is equal to the partial with respect to R of Y minus partial Q with respect to Z, the partial P with respect to Z minus the partial R with respect to X, and the partial Q with respect to X minus partial P respect to y. Now computing this using our vector field, this is equal, so again this is P, Q, and R. Partial R respect to y is 0, minus partial Q respect to z is 0, and 0, again, minus 0. Partial Q respect to x is 0, but the partial P with respect to y is 1. So the curl of H is equal to 0, 0, -1, which is not equal to the 0 vector. Meaning that this vector does in fact have a curl, and it's around the z-axis in the negative direction. So this is not irrotational, because it's going to rotate about the z-axis. We can compute its divergence though, and the divergence of H, again similarly to last time, is equal to partial P with respect to x plus the partial Q with respect to y plus the partial R with respect to z. In computing this using our vector, we have that this is equal to 0 plus 0 plus 0. So the divergence of H equals 0. So this is incompressible. Overall, in today's lecture, we determined what it means for a vector field to be irrotational and incompressible, and we defined what those terms mean. We also looked at two examples, one in which the vector field was irrotational but not incompressible, and the other in which the vector field was incompressible but not irrotational. Thank you all for listening. I will see you all next week for another video lecture.